In this section, we will look at measures of variation. The last section, we looked at measures of central tendency. What do we consider the center of data? But now we're going to look at variation, which is how much difference is there? Are all of the values in the set exactly the same? Are they really close to each other? Or do we have values from one end of the spectrum to the other? So the first measure of variation that we deal with is range, and we discussed what range is. Range is just the largest value minus the smallest, the maximum minus the minimum. It gives you a width of how wide your data set expands, encompasses. So we won't spend a lot of time looking at that. That's kind of a common measure. Another measure that we use is deviation. Deviation is the difference from the mean. Sometimes you'll refer to this as a deviation from the mean. So let's suppose we have a set of data. We'll just make up some numbers. And let's get the average here. If we want the average, remember the sample mean comes from adding the x values divided by the number of values. So if we add these together, 4 plus 8 plus 5 plus 10 plus 7 plus 2, we add our values, we get 36. We have 1, 2, 3, 4, 5, 6 data values. So the mean here is 6. So if we want the deviation from the mean, that is a distance. And to get the distance, we find the difference. So we want to know how far is a number from the mean. So we take that number and we subtract the average. So let's take these down a little bit. So put these in the columns. These are x values, and let's let the next column be the deviation. So if we take the first number minus the mean, notice we actually get a negative value. Negative because this number is below the mean. If we take the next number and subtract the mean, we get a positive value because that's above the mean 2 units. That's 2 units more than the average. 5 is 1 unit below average. 10 is 4 units above average. 7 is 1 unit above average. And 2 is 4 units below the average. So those are the individual deviations for this particular set of data. Now, after we talk about the individual deviations, then we have something known as the standard deviation. And there are 2 different standard deviations. There's a population standard deviation and a sample deviation. It's essentially the average, or it's related to the average deviation. If we wanted to know on average how far are these values from the mean, we could add up our deviations. Oh, made my bar too long. Add up our deviations, divide by the number of data points. But notice, if we simply add up our deviations, Some of these are positive, some of these are negative. Notice these two are opposites, so if we add those together, those cancel. These are opposites, so those would cancel. Those are opposites, so those would cancel. So if we just add up the deviations, it looks like our average deviation is 0. But if we're wanting to know the average distance that a value is from the mean, then when we're talking about distance, we're not really concerned is it above or is it below the mean. So instead of just adding up the deviations, we could take the absolute value of the deviations, add those together, and this would give us on average how far our data is from the mean. But another way of doing that, and remember the absolute value takes a number and makes it positive. Another way to make sure a value is always positive is to square it. Any number, if we square that number, we get a positive. So what statisticians have done is they've said, well, let's take the deviation, and to make sure that that is a positive number, let's square it. Now that changes how big the number is, but we'll deal with that in a minute. So if we square our deviation and add those together, then we can divide by n. And I'm going to change letters here. When we're talking about a sample average, remember the average of a sample, or the mean of a sample, we use x bar. But if we're dealing with the mean of a population, we use mu. So let's do this in terms of the population. So to get the standard, to get the deviation for the population, we square the deviations, we add those together, and we divide by n. But notice, once we square it, that changes the size of our deviation. So we call this the variance. And essentially the variance is the square of the deviation. So sigma stands for the deviation, or the standard deviation. Well, if we have something squared and we want to get rid of the square, we take the square root of both sides. So the variance is just the deviations squared, added up, divided by n, and then the standard deviation is the square root of that. Whatever we get for that calculation, we just take the square root of it. Now that's when we're dealing with the population. If we have every single piece of data, and we can take every single piece of data in the entire population, subtract the mean, and get the deviation. But sometimes we're only dealing with a sample. So if we're talking about a sample standard deviation, the formula is going to look very similar. We're going to get our deviation from the mean. We know this is in terms of a sample because this is x bar and not mu. We're going to square it to make it positive. We're going to add those together so we get an average distance, because we're getting an average distance from the mean. And instead of dividing by the sample size, we're going to divide by the sample size, instead of dividing by the size of the population, we're going to divide by the sample size minus 1. Now notice there's a difference between that and this one. Here, n is the size of the population. But when we're not dealing with the whole population, we actually subtract 1 from our size. So if we have a population, let's say n is 500, but we're taking a sample of 40, instead of adding up our 40 deviations squared divided by 40, when we square our deviations and add them up, we're actually going to divide by 39. And we're not going to go into an explanation of why that is, but that is called the sample variance. Just like the population variance was when we added up those square deviations, the sample variance is the same, just we're divided by n minus 1. So S here stands for the sample standard deviation. And most of the time when we're dealing with standard deviation, we're going to be dealing with the sample standard deviation. So just like with the population variance, if we want the standard deviation to get rid of the square, we take the square root of both sides. Because the square root of anything squared is itself. So the standard deviation in terms of the sample can be achieved this way. So let's do that for our little data set. We saw that if we just added up the deviations from the mean, those added to 0. So let's get our deviations squared. So if we square the first deviation, -2 squared is 4. The next deviation squared, 2 squared is 4. -1 squared is 1. 4 squared is 16. 1 squared is 1. -4 squared is 16. So our formula to get our sample variance, we add those together, and then we divide by 1 less than the sample size. So if we add these together, 4, 8, 9, 25, 26, 42. And earlier we said that those are 6 values, so we're actually going to divide by 5. So 42 divided by 5, so our variance is 8.4. So if we want the sample standard deviation, it's the square root of that. So about 2.898. Or about 2.90. So this is essentially the average distance that numbers are from the mean. The average distance x is from the mean. Now, for some notation, we will often refer to this as SS of x, or the sum of the squares of x. So when we hear the sum of the squares of x, if you just said that, you would think, well, the squares of x are x squared, and then add those up. But no, when we say the sum of the squares of x, we mean the sum of the square deviations. So our variance, remember, is that. So the sum of the squares of x divided by n minus 1. And then our standard deviation is the square root of that. Sums of the squares minus over n minus 1. Now there is an alternative formula for the sums of the squares of x that I'm going to use normally, and I would encourage you to use, because in this formula, when we do the deviations, keep in mind that sometimes when we calculate the mean, we get something that has to be rounded off, something that has lots of decimals. And if we round, then we're going to have a little bit of error. So each time we subtract that from our data value, that's going to have error. And then when we square it, then that's going to have error. And then we're adding a lot of things together that have error. So the more accurate way to get this value is to square each of your x's, add those together, add your x values together and square them, and divide that part by n. And we will get the same value with the possible exception of round off errors. So let's go back to our data, and let's copy it and do this calculation this way. So these are x values. We need to add those together, and I believe we already got that number. When we added our x values earlier, we erased that. And we added those together, we got 36. We also need to know what we get when we square them and add them together. So let's square each piece of data. 4 squared, 8 squared, 5 squared, 100 squared, or 10 squared, 7 squared, and 2 squared. So if we add those numbers together, that's the sum of x squared. So we have 16 plus 64 plus 25 plus 100 plus 49 plus 4, so 258. Those are the sums of the x squared. So our formula for the sums of the squares of x, instead of using the sum of the deviations, let's use the alternative form, sometimes referred to as the computational version. So we take the sum of the x squared. So when we squared our x's and summed those, we got 258. Now we take the sum of the x's. When we added our data values together, we got 36. That's going to be squared, and then we're going to divide by our sample size. So our sample size was 6. Now we have to be careful as we put this into our calculator. We have 258, and we're going to subtract the result of squaring 36 and then dividing by 6. So when we square 36 and divide by 6, we get 216. That's what we're taking away from 258. So for that, we get 42. So if we want our variance, it's the sum of the squares divided by n minus 1, so 42 divided by 5, which we've already done. 42 divided by 5, we said that was 8.4. So notice the numerator comes out to be the same whether we use this formula or this formula. But the second one, we don't have to subtract to get our deviation. In fact, we don't even have to know the mean in order to calculate the variance this way. And then we just square our data, add those, add our data, and we use those two sums. That gives us our variance. So if we want our standard deviation, we take the square root of that. And of course, we've already got that value. Now, when we analyze standard deviation, the larger the standard deviation is, the more spread out. So the standard deviation, which we said is roughly the average distance, let's say points are from the mean. So if the standard deviation is a small number, then values are grouped closely to the average. So let's suppose we had a distribution and we graphed it, and our distribution had an average here. If we have a small standard deviation, then our data is grouped closely together. But if we have a larger standard deviation, that means our data is more spread out. We still have the same average, perhaps, but our data might be farther apart. So, for example, if we have a set of data and everybody makes the same score, then there is no variance. There is no variation, no standard deviation. But if I have values all over the place, then I'm going to have more variation, so I'm going to have a larger standard deviation. And let's take a moment and look at how standard deviation plays into distributions. Often when data is collected, data will tend to group itself around an average value. For example, often when teachers give tests, there will be quite a few people make in the mid-70s or so. So as you get close to the 70s, you have a fair amount of data. But then the farther you get away from that score, then you have less and less data. You might have a couple of people make really high in the high A's, and then you might have a few people make really low in the 50s or 40s. But the closer you get to the mean, then the more and more data you have. So you may have heard of something called a bell curve. It was fairly common to hear people talking about grading on a curve, and that meant that they were grading in such a way that they had this bell-shaped distribution of grades, that most of the people were going to be around average, but if you did better than average, you're going to have fewer and fewer people. If you did lower than average, then your grades got skewed or got shifted accordingly. So this is called a normal distribution, or a bell-shaped curve. And if something is normally distributed, and if it is a bell-shaped curve, then it has some characteristics. If we are within one standard deviation of the mean, then we will have approximately 68% of the data. What do I mean by that? If this is the mean, and I'm just going to take the numbers off for now. if this is the mean, if we go one standard deviation above the mean, so the mean plus one standard deviation, or if we go one standard deviation below the mean, so the mean minus one standard deviation, then in that window, in that interval, we'll have about 68% of the data. So from there to there, it's about 68%, which is a pretty good chunk. Now, if we widen our range, if we go two standard deviations above the mean, so the mean plus two standard deviations to the mean minus two standard deviations, then everything in that interval is within two standard deviations of the mean. It's either at the mean or it's no more than two standard deviations away. So we're told that if we are in that window, that we have about 95% of the data. So almost all of your data is going to be within two standard deviations, but not every bit of it. So if we go a little bit wider, if we go three standard deviations above the three standard deviations below the mean, so the mean plus three standard deviations to the mean minus three standard deviations. So within three standard deviations of the mean, we'll have about 7% of the data. So by the time we get from three standard deviations above to three standard deviations below, that pretty much encompasses all of our data. Now, occasionally there are some values out of that window, 0.3%, but that's going to be something that is an exception, something that is an outlier. So that's what we mean by a normal distribution. It has to meet each of the characteristics. So one thing that we do occasionally is if we're given a set of data, we want to test, is it normally distributed? Is it a normal distribution? So we have to generate those intervals. We have to find out what is the mean for our sample, and then we have to look at the first interval. If we go from one standard deviation less than the mean to one standard deviation more than the mean, we generate that interval from knowing the mean and from knowing the standard deviation. And then we calculate what percent of our data is in that interval. So we just count up how many of our data points fall in that interval out of the total set of data, out of n points. And we make that a percent, and we check to see, is that about 68%? Now, if we only have 20 or 30 or 50 pieces of data, we're not going to get exactly 68% in that window. So often we're going to check to see, are we approximately a normal distribution? Are we approximately a normal distribution? So I might say you have to be within 5% of the empirical rule. So the empirical rule is what we talked about over here. This is the rule for being a normal distribution. So if we meet those three criteria, then we have met the empirical rule. If we check the first interval and about 68% of our data is in that interval, then we go to the next one. and we say, okay, if we are 2 standard deviations less or 2 standard deviations more than the mean, do we have about 95% of our data in that window? So we count, well, how much data in our set falls in that interval out of the total number in that set, make that a percent, and see, is that about 95%? If it is, if we've met both of those, then we keep on going and we check to be within 3 standard deviations. So we generate our third interval and we check to see, do we have about 99.7% of our data in that interval? So again, we're counting how many pieces of data are in that interval. We divide that by the sample size and see, is that about 99.7% within a little bit of error? And if it meets all 3 of those, then we would say, yes, it is a normal distribution. But even if even one of these fails, if we don't have these values for any one of these intervals, then it is not a normal distribution. So I believe there are examples of that for homework for you to check out. So that is typically normal distribution. And that rule that we use to check to see if it is a normal distribution, again, that's called the empirical rule. But there's another rule, or it's actually a theorem. It's called Chebyshev's theorem. And this applies to all distributions. So any distribution, regardless of the average and regardless of the standard deviation, this formula that we're going to have will tell us the minimum amount of data that is going to be in our error interval. So Chebyshev's theorem says that if K stands for the number of standard deviations, and the formula only works if K is bigger than 1, then for any value of K, we will always have at least 1 minus 1 over K squared. We will have at least that amount of data within K standard deviations of the mean. So what do we mean by that? So for example, let's suppose that K equals 2. So if we are within 2 standard deviations of the mean, so this could be for any distribution. It might not be a bell-shaped curve. It might be one that is skewed to one side or skewed to the other, or it might be a distribution that's all over the place. So for all distributions, this formula will tell us the minimum amount of data that is going to be in that interval. So if we do 1 minus 1 over K, so in this case 2 squared, that's 1 minus 1 over 4. If we get a common denominator, that would be 4. So if we subtract, that's 3/4, or as a decimal, that's 0.75. So what does that mean? That means at least 75% of the data for any set will be within 2 standard deviations. Will be within 2 standard deviations of the mean. So if we create an error interval that goes 2 standard deviations below the mean to 2 standard deviations above the mean, you're always going to have at least 75% of your data in that interval. Now you might say, well, I thought you said 95. 95 applies specifically if it's a normal distribution. Not all distributions are normal distributions. Some distributions are spread out differently. But for any distribution, regardless of how it's spread out, in what fashion, we will always have a minimum of 75% of our data in that error interval of 2 standard deviations below to 2 standard deviations above. If we look at 3, so if we put a 3 in, we get 1 minus 1/9, which, I mean, you can convert that to a decimal in your calculator if you want to. So 1 minus 1/9, about 0.8888. So that's about 88.9%. So regardless of our distribution, we will have at least 88.9% of data within 3 standard deviations. And this works not just for integer values of k. We could also put decimal values of k as long as we're picking numbers that are bigger than 1 for k. So this gives us a minimum amount. If I know how many pieces of data I have, I can find the minimum amount of data that is going to be 3 standard deviations above or below my mean. So that just kind of gives us a way of thinking about how much data is going to be close to the mean. As we get farther from the mean, how much data are we going to have left? So the farther we get away from the mean, the less and less you're going to have. You think about a city. If you go to somewhere like Birmingham, inside Birmingham, you have a dense population. You have lots of buildings, lots of apartments, lots of houses. You have lots and lots of people. But the farther you get away from Birmingham, then you still have metropolitan areas that still have a pretty good population, fairly thick. But the farther we get away into more rural areas, the less populous, the less dense the population is going to be. Same idea here. If we are really close to the mean, if we are within, let's say, 2 standard deviations, we're going to have a good bit of data. But the farther we get away from the mean, we're going to have less and less data. But as our interval gets larger and larger, we're going to be, if we just looked, let's say, in this loop, well, that's a good chunk of our data. That might be 75% of our data. If we go make our loop larger, we don't have as much data out here, but we are excuse me, we are accumulating more and more and more of it. So not as densely populated out here, but we're getting more of it. So all distributions will have sort of that type of pattern.